Adelante. Profesor, adelante. ¿Puede iniciar?
Sí. Ok. ¿Se puede compartir mi pantalla?
Sí.
Ok. ¿Puede emprender mi presentación? ¿O usted, alguna persona va a introducir? ¿Puede emprender mi presentación?
Sí, sí se puede ver. ¿Podría ponerlo en pantalla completa, por favor?
Sí, esta tiene pantalla completa. Tiene pantalla completa. ¿Por qué tiene problema? No sé. Tengo pantalla completas. Ok. Puede, es internet o otra cosa, no sé, pero mi pantalla es completa. Ok. Ok. Buenas tardes todos. Soy el doctor Kamala Cantorondo, una profesor tenure track en sección química del Departamento de Académico de Ciencia. Y estoy agradecido para los organizadores para darme una oportunidad para hablar con ustedes sobre mi investigación en electrochemical approaches for decarbonization of chemical manufacturing. Por favor, permítame para hablar en inglés para más claro. Okay? So now I'm changing to the English language. And so this is the content of my talk. And as we know that increase in consumption of fossil fuels for energy and manufacturing of commodity chemicals has led to exponential increase in global carbon dioxide emissions. And therefore, we are producing a lot of greenhouse gases by burning fossil fuels in our automobiles and also producing a lot of greenhouse gases from our chemical industries, particularly in manufacturing of commodity chemicals. And as a result, our ice cover in Antarctica is shrinking due to global warming. Therefore, there is a time has come to change from unsustainable thermochemical processes to sustainable chemical processes. So in this slide, I have noted down the production some chemicals, commodity chemicals, which are largest production volume, largest energy consumption, and largest greenhouse gas emissions. And you can see that ammonia occupies the top, followed by ethylene and methanol, propylene, BTX, and then others. Okay. And if you take the example of ammonia, for example, ammonia and all those CN chemicals, more or less, are contributing a lot to the global greenhouse gas emission. You can see these data. And other industry like mineral industry, metal industry, they're also contributing to the CO2 emissions. So in my opinion, all these processes, these unsustainable processes and the consumption of fossil fuel for these processes should be avoided so that we have a sustainable production of chemicals. For example, in case of ammonia, we know that the Haber-Bosch process is a revolutionary process which produces ammonia, and ammonia has a lot of use in pharmaceutical industry, in agricultural industries, and in producing the polymers also. However, if you see this process, Haber-Bosch process, it occurs at very high temperature and pressure. And further, to generate this high temperature and pressure, we burn the fossil fuels. And again, for getting the hydrogen for this process, we use the black hydrogen coming from the coal or the steam reforming of methane, which produce a lot of carbon dioxide and carbon monoxide. So for producing 1 metric ton of ammonia, we are releasing 1.9 metric ton of carbon dioxide into the atmosphere. Therefore, this process is unsustainable, and we have to change to a sustainable processes. And electrochemistry or electrosynthesis is the best option for this, because the inherent characteristics of electrochemical production offer unique advantages over conventional thermal directed processes. That is now the state of that process for producing commodity chemicals. If I count the advantages, number one is electrification of chemical production can be conducted at a small or medium scale with very high throughput. Okay, we can have distributed. For example, suppose we are producing some hazardous chemical, we can have an on-site production. So we can avoid the transportation of hazardous chemical from one place to other, because these processes, electrochemical processes, they can happen at ambient condition. You don't need very high temperature and pressure. So anywhere we can set up an industry. Okay, but thermochemical process, we need a specific space, specific area where we have high availability of raw materials and petrochemicals, so that we get them easily, so that we can reduce their production cost. But this is not for the electrochemical synthesis processes. Further, again, as electrochemical reaction is occurring at the ambient condition, we have high flexibility. Okay, and we can control the selectivity of product formation by applying potential. And electrochemical production of chemicals can easily be operated with renewable energy, because they need very little. It's not. It is very amiable current, little current or little bias to occur. So renewable energy can be integrated with these processes. Okay. And here I am giving you some common example of the products. For example, I have enlisted 2 products here, and if they are produced by electrocatalytic, biocatalytic, and fossil fuel derived processes, what will be their market cost? Okay. So if you produce ethylene, for example, by electrocatalytic process, and all the electricity is coming from the renewable energy, and electricity cost is 4 cents per kilowatt hour, and the Faraday efficiency is 90%, it will cost you $1,100 per metric ton. But when you do the same process in a biocatalytic way, biocatalytic is of course a sustainable process, but we have to engineer the bacteria. We have to engineer the bacteria to produce a particular product, and we need a clean room and a lot of things. Therefore, the process cost itself is very high. Therefore, the cost will be lie between 1,200 to 2,600. And of course, the fossil fuel derived are between 600 to 1,300, and the cost varies based on the availability of the raw material in a particular region. Okay. So, but if you can see the broader picture, that electrocatalytic or electrosynthesis processes and produce the commodity chemicals with an equal, more or less equal market price of the fossil fuel derived chemicals. Therefore, electrosynthesis is the best alternative to the current thermochemical processes. Before addressing the key technological challenges in the path of electrosynthesis process, let us have a look at some budding electrochemical technologies. We have a lot of electrochemical technologies still at the industrial scale, and they are producing like chloroalkali, electroplating. So they are already in the market, they are in industrial scale. But these processes are budding electrochemical processes which can give us the commodity chemicals. Okay, their current status is measured by a parameter known as technological readiness level, and it is a scale, and it has initial 1 and finally 10. It's just like a appreciation, customer appreciation parameter. Okay, and TRL4 is the lab scale going to the industrial scale, and above TRL5, the process goes to industrial scale. So TRL1 is just starting, it is process is at its infancy. Now people are optimizing the process parameters. And if you go up in the scale, you can transform the technology from lab to the market, to the industries. Okay. So electrochemical CO reduction for C1 products, for example, C1 products are CO, or syngases, CO plus hydrogen, or formic acid. Okay, they are at advanced TRL level. So we can do them easily at industrial current densities, and we can get a very high Faradic efficiency and energy efficiency of these processes. And startup companies are now taking advantage and of these processes. And a company named 12, it is in United States, and they are setting up the industry to produce syngas from carbon dioxide, and they are aiming to consume 1 ton carbon dioxide per day to produce syngas. Another industry its name is Avantium. It is a very advanced industry from Netherlands, and they are collecting the flue gases from the industries and separating carbon dioxide by pressure swing adsorption, and they are using this carbon dioxide to produce formic acid, and they are also obtaining a very good energy efficiency, and the market price of this formic acid is comparable to the market price of the formic acid produced by hydroformylation processes. Okay, so the technology is at the advanced level, but the CO2 reduction to C2 plus product is at TRL3. Okay, and therefore, why it is at TRL3? Because I will discuss some problems in my presentation. But it is a TRL3, and we have to bring to at least TRL5 or 6 to take it to the market. On the other hand, electrochemical nitrogen reduction is at its infancy. So it is a baby. So we are just starting the research on this. There are a lot of research on nitrogen reduction to ammonia, green ammonia. They call it ammonia verde, green ammonia. But the problem is ammonia. I will discuss the problem later. Latter part of the presentation, and there are alternate raw materials for this, like nitrates and nitric oxide, that can be converted to ammonia with a higher Faradic efficiency theoretically, but practically the scientists are trying to achieve a better energy efficiency and Faradic efficiency of this process. The electrochemical process of CO2 reduction to syngas using solid oxide electrochemical CO2 reduction cell was hyped by Haber-Bosch. For example, Haber-Bosch is a leading chemical company situated in Denmark, and they made industrial scale solid oxide electrochemical cell for production of syngas. But the problem with this is, again, this solid oxide electrochemical CO2 reduction cell requires high temperature up to 800 degrees Celsius. So again, for getting this high temperature, you have to use a non-renewable source of energy, and therefore it will not be environmental friendly, although it is at a very advanced TRL level. So what are the technological challenges? Okay, they can come from two things. One is chemical perspective, one is engineering perspective. Chemical perspective deals with the catalyst itself, and the engineering perspective deals with the electrolyzer. So coming to the chemical perspective, it is the Faradic efficiency. Faradic efficiency is nothing but what the charge you are giving and how much chemical you are obtaining, that we can convert it to the charges, and this is the efficiency. And the overpotential requirement, overpotential is the potential, extra potential that is required above the thermodynamic potential to perform an electrochemical reactions. And of course, energy efficiency is energy input by energy output at 100. Okay, so these parameters specially depend on the electrochemical reactions, inherent property of the electrochemical reaction, that reaction is feasible thermodynamically or not, how much free energy is required to perform that reaction, and on the catalyst also, how efficient is that catalyst, and how that catalyst can lower the activation barrier of these reactions. Okay, and the solution to this problem is lies in two things. One is rational design of the catalyst. And how can you design a catalyst rationally if you know what is happening during the reactions? And for this, we have to determine the reaction mechanism by operando spectroscopy, that is real-time monitoring of the reaction, see how the catalyst is changing, which surface or what type of shortage of the catalyst is responsible for a particular reaction. And also we can do this with density functional theory calculations. And this will give us an idea to design a catalyst which will be very selective towards a particular product with higher Faraday efficiency, lower overpotential requirement, and hence it will give us higher energy efficiency. For the engineering perspective, it comes to the electrolyzer. Okay, you design the lab scale the reactor, you perform all these reactions, and you are going to take it to the market. So you have to increase your production. For increase your production, you have to operate the cells with higher current density, and there comes the problem when you build a big electrolyzer. The first is mass transport limitation, and it is for the gas-fed electrosynthesis processes. For example, CO2 reduction, dinitrogen reduction, nitric oxide reduction. Here, these gases are have low solubility in aqueous electrolytes. Therefore, there will be a mass transport limitation. To get a better mass transport limitation, we can use an electrochemical flow cell. An electrochemical flow cell, the geometry of the cell allow us to operate this cell at higher current density. And again, when we operate at higher current density, we produce a lot of carbonates near the surface of the electrode, and that destroys the PTFE hydrophobic coating on this gas diffusion electrodes, and it causes electrode flooding. Suddenly, your current density drops after 200 or 300 hours of operation. So every time you cannot change the electrode and go for an industrial scale production by electrosynthesis. So we have to also think about a proper gas diffusion electrode. Okay. Then the process integration and stability. The process integration is if you integrate one electrochemical processes in an electrolyzer, you have to think about two things. What products you are getting, that's number one. And second, how stable is your catalyst during the whole electrochemical processes. Okay, for example, you are taking an electrolyzer. I will come to the configuration of electrolyzer later. You have a membrane in between, and you are producing organic compound like ethanol or methanol, and they can easily digest the membrane in long term. So there the problem starts. Your membrane is getting destroyed, your cell will short circuit. So the process integration and proper selection of the membrane is important. And for organic electrosynthesis that occur in organic solvent, the ion conductivity is the issue. And again, when we are operating the cell at higher current density, there is a lot of heat generated. We have to do the heat management. The solution is to standardize and make a continuous flow electrolyzer, and we have to identify suitable membrane for a particular processes. We have to make better gas diffusion electrodes so that they can resist higher current densities. And further, we can use MEA electrolyzers. And the other thing is to get high value hydrocarbons. For example, hydrocarbon having more than 3 carbon atoms, the electrosynthesis can be coupled with other complementary processes like hydroformylation or biocatalytic process, so that we can get a hydrocarbon in a sustainable way. Of course, it will increase the cost, but it will save the environment. Okay. So now my research is focused on pollution to solution. So I am using the pollutants and abundantly available water as feedstock to produce commodity chemicals. That is, we can use carbon dioxide, whatever we are producing, in an electrolyzer to produce hydrocarbons and fuels. And also, we can use the nitric oxide that are being produced from industrial wastes. And nitrate is a major water contaminant nowadays in water, and it is affecting the bird population, and it is affecting the cycle, the gynec problem in women also. Therefore, we have to treat the water, and instead of removing the nitrates, if you can convert the nitrate into green ammonia, that will be a better way to go for a circular economy. Okay. Now, I am coming to the process. The electrocatalysis, which can be instrumental for decarbonization of chemical industries. So what is the electrocatalysis process? Electrocatalysis may be defined as the relative ability of different substances when used as electrode surface under same conditions to accelerate electrochemical processes. And for electrocatalysis, we need at least 2 electronically conducting electrodes, and an ionically conducting electrolyte. And by applying certain bias, we can generate new compounds at or near the surface of the electrode, and by default, the cathodic product and anodic product will be separated. Okay, and this is the diagram of an electrolyzer. You have a anode, you have a cathode, and if you enlarge this area, here you have a gas diffusion electrode coated with anode catalyst and gas diffusion electrode coated with cathode catalyst, and in between you have a membrane. Okay, so this is the electrolyzer, and anode generally we do water oxidation, and cathode, for example, we can do CO2 reduction, nitric oxide reduction, or anode we can do some organic electro-oxidation reactions. Okay, so this is generally the electrocatalysis process. And I have already discussed the advantage of the electrocatalysis. So coming to my first work on electrochemical CO2 reduction, the electrochemical CO2 reduction was first reported by Hori in 1985 when they used the copper electrocatalyst and they performed the electrochemical CO2 reduction, and they obtained syngas, methane, ethylene, and some hydrocarbons. Later, they have tried a lot of metal electrodes, and they obtained different products on different metal electrodes. With and the best material for this is copper, because copper shows better selectivity towards C2 plus product in CO2 electro reduction. Okay, that is the main aim, to obtain the C2 product. It depends on the binding energy of the metal to the intermediates. Okay, I am not going into much chemical or technical details of these things. Then before designing a catalyst, we have to learn what is occurring at the electrode surface and what is occurring at electrode-electrolyte interface. Because if we keep an eye on these processes, this will help us to design a better photocatalyst. The electrode surface in particular, it is not plain. It consists of lot of defects and lot of facets. Okay, and the facets and defects, they have each defect and each facet has a particular arrangement of atoms, particular coordination number of the surface, and particular configuration of the surface, and it can give bind to an intermediate selectively and can give you selectively a product. Okay, in CO2 reduction. And the reaction occur at electrode-electrolyte interface, and electrolyte interface has a galaxy of processes happening at the electrode. The required redox reaction, then the catalyst oxidation and reduction, some adsorbents, anions will get adsorbed on defects and surface of the catalyst. So all these processes are occurring simultaneously. So we have to design a catalyst in such a way that we can expose a specific facet and we can obtain a specific product. For example, if we synthesize a catalyst with copper 111 surface, we will get specifically methane from CO2 reduction. And if we go for 100, we'll get C2 products like ethanol and ethylene. Therefore, nanostructuring of the catalyst and identifying the facet of the catalyst that can give us a particular product is important in catalyst design. By keeping this idea, we designed a catalyst for electrochemical CO2 reduction on copper surface. Okay, copper is generally oxidized in the atmosphere, so there is a layer of very thin layer of copper oxide. It is not intentional, but it is a natural process. Okay, so we took copper foil and we do electrochemical cycling so that we develop two kinds of nanostructure. Okay, in one nanostructure, we develop horizontally aligned nanowires, and in other nanostructure, copper nanostructure B, we have grown nanowire perpendicular to the surface of the copper. Therefore, we expose two different kind of facets, as can be concluded from XRD. For copper nanostructure A, we have one facet predominantly, and for copper nanostructure B, you have predominantly 100 and 110 facets. Also, we determine the facet by electrochemical methods, and also the nature of facets could be revealed by linear swing voltammetry, where if you see the CO adsorption peak in CO2 for the electrolyte, you have a better CO adsorption on 111 surface than 110 surface. Okay, so all the electrochemical characterization and structural characterization, so that we have in copper nanostructure A, predominantly 1-1-1 facet, and in copper nanostructure B, we have predominantly 1-1-0 facet. Okay, and we, for a quick identification of product distribution, we employed a differential electrochemical mass spectroscopy, and we identified it is nothing but a electrochemical cell connected, interfaced with a mass spectrometer and connected to the potentiostat or galvanostat for apparent potential. And we obtained methane as we have in copper and nanostructure A, major 1-1-1 facets, and we obtained mixture of C1, C2, and C3 products on copper nanostructure B, and the concentration of oxygenate was about 41%, and we can see here also that the copper nanostructure A only gave us the C1 products, no C2 products was obtained, but here we obtained C1, C2, and C3 products. Okay, but the product selectivity is there is no particular product selectivity here because the Faraday efficiency of the product formation is just intermediate. We don't, although copper nanostructure A is highly selective for production of methane, which we did not wanted in the beginning. We were designing the catalyst for oxygenates, alcohol production, but we end up with methane here, and here even we are getting alcohols. The Faraday efficiency is very low. Okay, so therefore, another thing we have investigated the catalyst surface structure before and after electrolysis, and as you can see that copper 1-1-1 surface changes drastically during the electrolysis, and you obtain a totally a different set of facets after electrolysis. But copper 1-0-0 surface or copper 1-1-0 surface, it is more or less stable, and there is a very marginal change after the electrolysis. We'll come to this fact later, the changing of the electrode surface during the electrolysis, how it can be a bane, it can be a good thing, or it can be a bad thing in electrocatalysis. We'll come to know about this in my later slides. Okay, then we were thinking about electrifying ethanol production, producing ethanol from CO2 by electrocatalysis, because bioethanol production still has some carbon footprints, and we wanted a zero emission ethanol production. But the problem lies in the reaction mechanism. If you see the selectivity map, ethanol versus ethylene, lamentably they both proceeds via similar mechanism, and only they bifurcate at the last step, giving ethylene as the major product on copper and ethanol as the minor product. So to enhance the product selectivity, we found a paper. They discussed the process of tandem electrocatalysis. Here they produce coupled a CO forming catalyst with copper. So the job of CO forming catalyst is it do CO2 reduction, it performs CO2 reduction and convert it to carbon monoxide, and the carbon monoxide gets spilled over to the copper surface and combined with CH2 to produce ethylene. Okay, but the problem is, if you in theoretically it looks correct, but when practically you saw the Faraday efficiency of product formation, you are ending either with higher concentration of carbon monoxide, this black, or you are ending with higher concentration of hydrogen. But although you are improving the ethanol formation over ethylene, but we are not getting appreciable Faraday efficiency for ethanol formation. So we thought why it is happening, because we know that gold, silver, platinum, they are very good catalysts. And if they are coupled with another metal, whatever metal that is, they will not leave their properties, they will produce CO. So CO is produced more than the CC coupling on copper surface. Therefore, we are obtaining higher amount of CO. And of course, hydrogen is the competitive reaction to CO2 reduction. So we are obtaining a lot of hydrogen. So what we did is we went to the literature and we found that carbon nanomaterial can convert carbon dioxide to carbon monoxide. So we adopted a standard electrocatalysis technique, but we designed copper nanocubes on copper electrode surface and modified with the graphene, reduced graphene oxide. And also we increased the thickness of the reduced graphene oxide layer to see the effect of the thickness of the graphene oxide layer on C2+ product selectivity and ethanol selectivity. Okay, And we confirmed the presence of the graphene layer by Raman spectroscopy and XPS spectroscopy. The main thing in this slide to look at is that there is a charge transfer from RGO to the copper surface, and therefore we are getting a copper oxygen signal here. And this shows that we have a subsurface layer oxide in the electrocatalyst, which is helpful in ethanol production. And we did this normal electrochemical characterization. And when we did the CO2 electrolysis, you can see that this RGO modified copper oxide copper nanocubes gives us the Faraday efficiency of ethanol 76% at minus 0.9 volt versus RHE. And here you can see the oxygen selectivity over ethylene. It is drastically enhanced. Okay. And we compare our results with the existing catalyst in the literature, and you can see that our catalyst is one of the best catalysts that can produce ethylene from CO2 reduction with high Faraday efficiency. So we did spectroelectrochemical Raman characterization to see why we are obtaining higher amount of ethanol over ethylene, and which species is responsible. So we find the difference is in this region of the spectrum. Okay, Raman spectrum. So we did this spectrum by applying the potential and monitoring the formation of the intermediates through spectroelectrochemical Raman spectroscopy, and you can see that at minus 0.9 volt, this intermediate is forming. And this is the potential where we are getting higher amount of ethanol. Then when we saw the DFT calculation in the literature, we found that this corresponds to this kind of intermediate. So we concluded that the presence of graphene or reduced graphene oxide on the surface of the electrode is driving the last step of this reaction towards ethanol, and we are not getting this kind of intermediate, so ethylene production, or we are getting less kind of this intermediate, so that ethylene formation is hampered. So by applying this process, and we can scale up this to the industrial current density to obtain selectively ethanol from CO2 electroreduction. And this is the mechanism that I was talking about. The CO2 is first reduced to carbon monoxide, and carbon monoxide is then combined with another CHO molecule on copper surface to give you ethylene. To give you ethanol. Okay. Also, we produced a higher amount of ethylene on corner truncated copper nanocubes. And you can see that the copper nanocubes, which is corner truncated, has a higher amount of 100 facet, and there is some fraction of 111 facet, and this is actually assisting in the formation of ethylene, and we got around 60% Faraday efficiency of ethylene in CO2 electroreduction process. Then, as I was talking, that the catalyst surface is continuously evolving, is dynamic, it is changing during the electrochemical reaction. So, and it is being proved by the studies from Professor Cunha using an in situ liquid cell transmission electron microscopy during the electrochemical CO2 reaction. But they could not do the real-time product evolution, product selectivity measurement during the electrochemical CO2 reduction reaction on copper nanocubes, and they could not show the temporal evolution of product formation. So what we did is we adopted this technique, differential electrochemical mass spectroscopic technique. Very few people work on this, and this is a paper vacuum quadrupole mass spectrometer coupled with a potentiostat and interface with the electrochemical cell, and every group developed their own DEMS setup. So the credit goes to Professor Fabio Lima in University of Sao Paulo, who developed this DEMS setup for analyzing electrochemical reactions. And I think there is one group in the United States and 2-3 groups in Europe, those who are working on DEMS. No other group has a DEMS facility for CO2 reduction reaction. So because why this is unique, I will come to later. First, we have a vacuum pump which is connected to the working electrode. So as soon as CO2 reduction occurs, it sucks the product and take it to the ionization chamber of the mass spectrometer. And here electron ionization occurs, and we can direct the detector, quadrupole detector, to choose the mass fragment we want, a specific mass fragment for a specific product, and it will plot the current density of that product. Okay, when you see the data, you will be more clear about that. And for example, and also we studied the structural evolution of copper oxide nanocubes. So what we did, we took the first linear sweep voltammetry before electrolysis. Then we performed 10 minutes of electrolysis at 10 milliampere per centimeter square. Then we studied this linear scan voltammetry second linear scan voltammetry. And this is the curve from the potentiostat. Okay. So this is, we call it Faraday current. And Faraday current is a average out current. It is current corresponding to all the processes occurring in electrode and electrolyte interface. But when you come to an ionic current, it is a product specific current. Product specific current means it is specific to a particular product evolution, because we are directing the mass spectrometer to record the signal of that mass fragment. For example, and this mass fragment is unique to this product. It is not overlapping with other. So we have to choose mass fragment in such a way that it should not overlap with other products. Okay, so you get a unique contribution of the mass current to a particular product. And here we can see from the nature of the onset potential that alcohol and ethylene formation, they occur via similar mechanism, as they have similar shape of the crop and similar onset potential. And on the other hand, methane formation, it has a different onset potential and different shape of the curve, therefore it occurs via another mechanism. Okay. Further, we did cyclic voltammetry, and we could identify here that the copper surface is changing during the electrocatalysis. For example, here if you can see, when we applied 10 milliampere per centimeter square, we obtained a bias of minus 1.2 volt. Hydrogen production started instantly. But if you see the CO2 reduction, it started with a delay. That means catalysis is taking 30 or 40-second time under applied potential to reorganize itself for CO2 reduction. Again, when you see the increasing of the currents, it increases up to 110, 120 seconds, and it was getting stabilized in case of ethylene, but for ethanol, it grows continuously. Okay, that means the ethanol production is increasing with time, whereas the ethylene formation is getting saturated after starting of the electrolysis after some time. Okay, and if you see the cyclic voltammetry, you see the similar piece of information. You do a multiple cyclic voltammetry. This is the first cycle, this is the second cycle, and this is the third cycle. So here you can see that, of course, hydrogen will be produced in a very high amount, because in the setup is not designed for mass transport limitation things. Okay, so if you see the CO2 reduction product, you can see a drastic difference between C1 methane and ethylene and ethanol. We saw that after the first cycle, under successive cycle, so C1 product formation is decreasing, and C2 product formation is more or less constant. And we did not get any of the CO here, because all the CO are getting coupled to forming C2 plus products. And therefore, we concluded that maybe after 10 or 15 minutes of electrolysis, the C1 product formation stops completely, because you can see the peak of the product is decreasing, and C2 product formation is getting enhanced. From this study, we concluded that the copper 100 surface in copper nanotubes are getting better with passage of time during electrocatalysis process. Further, we could find a hysteresis in case of C2 products. There is no hysteresis in case of hydrogen or C1 products. Hysteresis means your anodic sweep don't coincide your cathodic sweep, and there is a little gap between the anodic sweep and cathodic sweep. That's different in onset potential. It is due to the absorption of CO2 reduction intermediate, and you have a longer lived intermediate in case of ethanol than ethylene. So these are the conclusions we can obtain from the DEMS measurement, and it will direct us to get a new catalyst with a specific facet and specific ratio of the facet, which can give us a specific product. Okay, and now coming to this, all the above works were being done in Pontificia Universidad Católica de Chile, and here with the help of my department and with the help of Matter Hookpay Research Group, Professor Andres, I am going for photoanode driven electrochemical reduction of nitric oxide. Okay, why we are going for nitric oxide and nitrates, not dinitrogen? Because dinitrogen bond is non-polar, it's not polar, and you cannot break this bond easily, and the solubility of dinitrogen is very low in water. On the other hand, nitric oxide and particularly nitrate, it has high solubility and bonds are polar, so it is easy to break, and we can make new bonds and produce green ammonia. For this, we are, as I say, I'm working with Professor Andres Guerra from Physica and Professor Andreas Boone from Technical University Limonau, and for operando characterization, I am working with Professor Mauricio Isaacs from Pontificia Universidad Católica de Chile. Okay, and we are designing this kind of reactor where it is a photoelectrochemical reactor, and we have a photoanode where we do water oxidation, but we generate a photovoltage at anode, which will supplement to the photovoltaic with the voltage applied at the cathode. So we have to apply low voltage. For example, if the nitric oxide reduction require -1 volt potential, okay, -1 volt, and we are doing a electrochemical reaction, we have to give -1 volt. But if we couple that with a photo electrochemical process, we have to supply like -0.6 or 0.7 volt. Other voltage will come from the bias generated in or photovoltaic generated due to excitation of the electrons in the photoanode. So the process will be driven by the photovoltage of the photoanode. Therefore, we call it a photoanode driven electrochemical nitric oxide reduction reaction. Okay, so this electrolyzer design will be collaborated with Professor Andreas Boone, and we have this photoelectrode production will be done by magnetic sputtering in Professor Andres' laboratory, and in my laboratory at chemistry, I am producing the copper oxide nanostructure and other metallic nanostructures which will be employed in the reduction of nitric oxide and nitrates to green ammonia. And the aim of this process is not stopping at ammonia, we'll go for production of urea, and also we'll go for production of CN containing compound and fuels like hydrogen and methyl hydrogen in future. But our principal aim now is to produce ammonia, and we have already started the work. Okay, and also what I was telling that we can couple the electrochemical process with thermocatalysis process to get high value chain hydrocarbons. And this is the work which was published recently, and it is a proof of concept for the process. And another thing is, I talk about the paired electrolysis process. We know that in any electrolysis process, the anodic process is coupled with the cathodic processes. And we are interested in cathodic processes, for example, in CO2 electroreduction, nitrogen reduction, and hydrogen production. We are interested in cathodic process. So the oxygen that is produced in the anode is left into the atmosphere. Okay. So, but the process energetics, if we talk about the energetic of the process, the total cell voltage is the contribution from the reduction of reaction, from oxidation of reaction, and the cell resistance. And this water oxidation reaction is thermodynamically unfavorable, kinetically sluggish, and therefore it accounts for very high cell voltage, and it is uneconomical. But if we replace this thermodynamically unfavorable reaction with a thermodynamically favorable electrosynthesis reaction, for example, glycerol oxidation or HMF conversion or alcohol oxidation, then we can save a lot of voltage. For example, the cell voltage is becoming 1/3. Here we are getting cell voltage, we need cell voltage 1.33 volt, but here if you pair with another process other than water oxidation, for example, glycerol oxidation, the cell voltage is decreased by 1/3. Therefore, the energy efficiency will be theoretically increased to 3. It will increase But theoretically, we can say that there will be at least 3 times increase in energy efficiency just by changing the anodic reaction. Okay. Therefore, I have written a review where I identified the reactions and also the process parameter, process optimization for CO2 reduction and hydrogen production processes. And this review is published in 2020. And we are also going to apply this concept after we get a very good parametric efficiency for ammonia. We are going to change the anodic oxidation reaction from water oxidation to say alcohol oxidation or glycerol oxidation. Okay. So this is the plan of my research in Cookpay. So in conclusion, I will say that in the summary of the conclusion, I will say that if we design a good catalyst with a particular surface, and we can get a product selectivity, and the catalyst will be able to reduce the overpotential of the reaction due to the selective binding of the intermediate to that particular facets. Okay, and also we are working on the reactor design so that we can operate this at industrial current density, and the main of our research is going from lab to the market level. Okay, and this is the outlook of electrochemical synthesis process. So what we have to do to make electrosynthesis process cost competitive, and it can be the major production process of commodity chemicals, so that we'll go to the circular economy. The first is we have to establish renewable electricity. A lot of renewable electricity is necessary for electrosynthesis process. Okay, and this renewable electricity should be cost less than 4 cents per kilowatt hour, so that we can produce our commodity chemicals with a cost competitive with the current chemicals that are coming from the petrochemical industry or thermochemical industries. Okay, and we have to develop mature technologies of flow electrolyzers that can operate at high current densities with energy efficiency minimum 60% or higher. Then for getting higher value chain commodity chemicals, we can couple electrochemical processes with biocatalytic processes, and we can get high value added chemicals. So for example, if we know that the production of C1 products is at advanced TRL level, technology readiness level. So what we can do is we can couple this CO production with a hydroformylation reactor, and we can produce other oxygenates and other hydrocarbons with high carbon value. And also we can exploit the biomass of upgrading. Okay, biomass is like petrochemical, it contains a lot of hydrocarbons. So we can upgrade this biomass in a electrochemical biorefinery to get the value added products out of it, and it will also help us to reduce the dependence on fossil fuels. And also we can upgrade the presently available commercial electrolyzers with the pair electrolysis process, so that we can have a value addition and we can have higher energy efficiency. And last but not the least, government should make policies that promote social, political, economic incentive to transition to low carbon processes. And I want to mention one more thing here is that our Vice Rectory of the investigation, they are in constant contact with various industries. So we can do a process, or government can pay money to develop a lab scale process. But from going from lab to industrial scale process, we need the intervention of industries. And in our case, we need Repsol and Enel. For example, if you see Enel has already started establishing a green hydrogen production industry from water electrolysis in Chile. So the same thing, and for that, he did the Enel took the help of University of the Chile and Pontificia Universidad Católica de Chile. So they sat together on a table, they developed the technology, and they are now going solely towards production of green hydrogen. The same way we can do it in Peru. So I request the Vice Rectory of Investigation to facilitate this meeting between the industry and our research group so that we can have more funding to develop better electrolyzers in near future. Okay. And I acknowledge my research group and my Professor Mauricio Isaacs and Professor Tom Welton. He is a collaborator in nanocellulose project. And there are some of people are missing from my research group in Chile for the work of CO2 reduction. And I also acknowledge both the universities for their constant support. And specifically, I acknowledge my Department of Academic Science here, and the head of the department, the director, Francisco Ugarte, and Professor Yves Coelho for his unconditional constant support. I acknowledge my colleagues of the department here and from physics who has cooperated with me selflessly to develop my research goals. And I am grateful to the Grupo de Ciencia de Materiales y Energía Renovable to give me a place in the group and give me the infrastructure of the group to perform my research. And I acknowledge my collaborators from various universities who helped me to perform in situ spectroelectrochemical studies and DEMS measurement. And last but not the least, I thank all my audience for their patient hearing, and thank you for your talk. And I welcome any suggestion and question on electrosynthesis processes. Thank you. If anyone has any question on the process or on the topic, please ask me. And I need your suggestion to improve my research also. What is the activity in rural town for fomented circular economy? So, as I told you that the electrochemical processes can be set up in a small scale. Okay, you can just take a stainless steel tank and separate it for a small scale process, very small scale process. You can take a stainless steel tank, put 2 electrodes, and in the between you put a membrane, or even you can put a frit, or you can put a separator, and you can produce chemicals. So you can establish a plant at a very reasonable price in the rural town. And also the rural community, they produce a lot of biomass in the wood. For example, they produce wood. You can extract lignin from the wood, and you can set up a electrochemical biorefinery and convert this lignin to different chemical products, and hence you are going to the circular economy. Okay, so electrochemical process can be applied in the large scale, in a small scale, and it can collect it can go for various raw materials like industrial gases, starting from industrial gases to the rural waste. Even you can get waste energy from the waste also, even energy from toilet water. People are trying to produce energies. I don't know what are the technologies, but they are purifying the water and producing the energy from there also.
Thank you, Kamala. I am impressive for you show this your work. You say about the electricity, the monophasic, is monophasic or triphasic the electricity what you need in this process?
Yeah, I need normal electricity like that is coming from our plug point.
Monophasic.
I think it. I don't know about the physics of the electricity, but you can use the normal electricity what is coming, but it should be produced from renewable energy and injected into the grid.
Okay. Yeah,
So
because in rural town is difficult, especially for big industry. Maybe need the triphasic for.
yes,
It's very complex. Yeah, but I need to understand because it's potential for rural towns in this moment for a circular economy. Yeah, it's a very important project. It's because but for me, so yeah.
I understand the constraint, and I think you can in the rural for practical purposes. I don't know about the phase of the electricity, but if you can light a bulb with that one phase electricity, you can operate an electrochemical cell. It's simple. You don't need very high amount of electricity to run an electrochemical process. Yes, if you want efficiency, if you want more production, you want to ramp up the production. Yes, you need more electricity. But simple electrochemical processes that can be run around the voltage requirement, for example, for lignin, you can do it at my 1.8 volt. It is minimal. It's not very high. Take a potassium hydroxide solution, separate lignin from wood, and you can operate at 1.8 volt, and you can get some vanillic acid or some other acids. And also, if you take hydroxymethyl furfural, like compound, you can isolate from sugar. So you can dehydrate sugar and you can get hydroxymethyl furfural and you can convert it to furan dicarboxylic acid and it can be used in bioplastic. For CO2 reduction, you need a little bit higher infrastructure than biomass oxidation. So I think in village, we can start with biorefinery and go forward. You are welcome, Professor Amirada. Thank you, Professor Rosario. Thank you.
Profesor Kamala Canta, muchas gracias.
Yeah, de nada.
Si ya no hay más preguntas, podríamos dar finalizada la
Sí,
conferencia.
claro. Muchas gracias.
Muchas gracias. Muchas gracias a todos los participantes.
Ok. Voy a salir. ¿Dónde estás?